Our second speaker is Professor Andrew Dagolo, and from maybe University of Padova, and he is a recipient of Frontier Science Awards. I think it's a related talk. The title is on the irregular remote correspondence. Let's welcome.
Yeah, I cannot even learn how to turn on a microphone, sorry. Since it is recorded, let me remind that it is from a joint work with Masaki Kashiwara. And I was just reading I should also thank the organizers. Okay, so the original formulation of the problem was to find a Fuchsian differential operator with prescribed monodromy. And then people asked, what if we add on top of it also the Stokes data? Can we find an operator whatsoever? And now I jump to the modern formulation. X is now a complex manifold of any dimension. I denote by OX the sheaf of holomorphic functions, by DX the sheaf of algebras of linear differential operators of finite order. And then there is this theorem. Again, don't look at the red part. The black part is due to Kashiwara in 84. There is an equivalence of categories, which is compatible with Grothendieck operations of tensor product, pullback, push forward, under suitable assumptions, and dual, which goes from regular holonomic D-modules into perverse sheaves. So as this is the section on D-modules, I cannot tell you what's the definition of a D-module, but for those who don't know, I just noticed that holonomic D-modules are a kind of higher dimensional analog of a single ordinary differential operator, different from zero, and the regularity is the analog of the Fuchsian condition. Also, for those who don't know, perverse sheaves can be misleading. Actually, those are objects in the derived category of sheaves, and that is why I allow myself to take the full derived Ohm functor in the category. And so the idea is that if you compute solutions, solution in this setting means Ohm with values in holomorphic functions, then you get something which is perverse. This op here is because the solution functor is contravariant. And then you can ask the same question as before. So what if we drop the regularity condition? And then the aim of this talk is to try to convey some taste of what Kashiwara and I propose. So to add a couple of adjectives, you need to consider sheaves which are enhanced and subanalytic, two things that then we will merge together. And if then you construct in this setting a new sheaf of enhanced tempered holomorphic functions, the only thing you have to do in order for the equivalence to hold is to put this T. Okay, so disclaimer, in blue, that's another color code. I write things which are not necessary for understanding the talk. In fact, this is a fast way of presenting things. Unfortunately, we were not able to give a nice topological description of the target category, which was the problem open for several years. Okay, so but now in order to describe for you what it means to be enhanced and subanalytic, I want to go back to the original formulation in one dimension And I will go on giving examples, very easy examples in dimension 1, even real dimension 1. So first of all, let me go back to the 1970, when Deligne gave the first categorical formulation of the Riemann-Hilbert problem. Again, don't look at the red part. He took meromorphic functions with poles on a hypersurface D, and he proved that if you start from regular flat meromorphic connections, then you can reconstruct them through the same solution functor, but only looking at what happens outside of the divisor, which is now fixed. Before it was not fixed. And it's enough to consider a local system. So the advantage of this formulation, in order to explain things, is that we are no longer in the derived category. These are ordinary sheaves which are locally constant of finite rank. Okay, and how does this theorem fits in the previous statement? If instead of considering any holonomic module, you bound yourself to consider only those whose singular support is contained in the divisor, and moreover, modules which are so-called localized around at the divisor, so which are stable by tensor product with the meromorphic functions, then you realize the category of flat meromorphic connections as a full subcategory of the previous one. So you recover this from Kashiwara theorem. I'm not claiming that, okay, so Deligne gave an independent proof. He's also dealing with the algebraic case, which I'm not talking about today. So anyway. Now let us really go back to ordinary differential equations. So for me, X will be just an open subset in the complex line, a neighborhood of the origin. The origin now is my divisor. So let me take a linear differential operator, I call it P. It has some holomorphic coefficients. I denote by delta the holomorphic derivative. I want the order to be effectively M of the operator. So I want that the top degree coefficient is not identically 0. Actually, I want that it has precisely the origin as the only 0. Okay, if you want to fit this operator into the setting of holonomic modules, you associate to it the cyclic module with an annihilator ideal generated by P, that's the left D module, and then it is not localized in general, but you localize it, that's a projector, so I project it in this category. It's an easy fact to check that in this case, the solutions, when you restrict outside of the pole, of the singular point, are simply the set of what all people would call solutions. So you solve the homogeneous equation P of U equal to 0. And then if you use the Cauchy problem that you learn as an undergraduate, it's easy to check that this is indeed a local system of rank n on the complement of the divisor. Okay, so now the question is, look at the red piece. If you drop the regularity condition, of course, it fails to be an isomorphism. I just put parentheses. Now the idea is what kind of data should I add to the local system in order to be able to reconstruct a connection which is not necessarily regular. And so I go back and recall some classical results on formal and asymptotic solutions due to Fukuhara, Levelt, and Turetti. The proposition is in 2 parts. First, let me talk about the formal solutions at the origin, which is our singular point. I'm sorry, but this slide is a little bit heavy with symbols. The structure is the following. So since my operator has order M, I want to find M independent solutions. I put a hat to remember that those are only formal solutions. There is an exponential, there is Z to some power, and then with possibly logarithms, there are some formal power series. In the general setting, you need the ramification. So actually, things are not written in terms of the variable Z, but in terms of the diff root of Z. And then the exponents, which are called exponential factors, are polynomials in the 1 over the root. And then lambda is an arbitrary complex number, and the coefficients of the logarithms are formal power series in the root of the variable. A, J, K, L are just constants. Okay, this is at the level of formal solution. Now there is some red appearing because I add one. If instead of considering the full power series, you stop at a certain given level, n, then let me denote by U hat n what you get. So since now there is no more formal piece, you can give a meaning to that, but not all over, because there is also ramification. So you need to choose a determination of the monodromy and then also the root and power lambda. So, but you can do that on a sector. So the notation is that I pick a direction. Direction, I mean, it means that I pick a real number and then I take e to the I theta on the complex line. This direction emanates from the origin, and you can consider a small sectorial open neighborhood of this direction, which is small enough so that this fact holds. You keep the same formal solutions as above, and you can find the basis of true holomorphic solutions defined on this open sector, which is asymptotic to the previous one in a precise sense that I recall here. So now I repeat, if you consider u at n, it makes sense in the sector. So the difference makes sense. And I want that for each n, you can find a constant such that this difference is bounded by what you would have on the next missing term. Okay, so it's the exponential and then z to the lambda plus what's left. And actually, a very elementary but very important consideration is that the absolute value of the complex exponential is precisely the exponential of the real part. So the key part is to look how things are ordered with respect to this special kind of order. It's not totally an order because things on a sector can be neither smaller or equal one than the other, nor bigger or equal, can really be uncomparable, okay? But what you note is that if you consider two exponential factors, one smaller than the other, then in fact, you can notice that you don't have uniqueness at all here, because if you add any solution attached to a smaller exponential factor, then if you look at the equivalence relation, since there is rapid decay, you don't see at all the component UK. Okay, so this is an important point. This is the ramification order which is attached to sorry, I no need to change slide. No. Is so I will give an example. Next page. For example, first, you can already look at the example there, which is the original picture that Stokes drew in 1853. But I come back to that later. So what are the Stokes data that were mentioned in the first slide from Wikipedia? So the Stokes data consist in two things: exponential factors that I just discussed, and Stokes matrices. How do you boil them up? That's the recipe. First, you fix a basis of asymptotic solutions at the origin. Then you cover a puncture neighborhood of the origin with finitely many small enough sectors overlapping 2 by 2. And then on each of those sectors, you choose an asymptotic solution in the previous sense. So for example, if you have another sector, v theta prime, I call u prime j the asymptotic solution, always to the same formal solutions. And then you notice that on the overlap, you see two different bases. So of course, there is a constant matrix interchanging one with the other, and that's precisely called the Stokes matrices, Stokes matrix. A fact which follows from the fact on the previous slide is that this matrix has the property that if you see some coefficients which is non-vanishing, then necessarily the corresponding exponential factors are ordered in that sense. And so I repeat, I copied here the picture that Stokes drew in 1853 precisely to keep track of this order relation, because he was interested in the Airy's differential equation, which is of order 2. It is irregular at infinity, in this case, not at the origin. And in that case, the exponential factors that he found turn out to be what's written here. And you see, answering to Alexei, you see a coefficient 3/2 already in the Airy function. And actually Stokes realized that there was some phenomenon happening because, in fact, this operator has no singularity whatsoever at finite distance. So it has a basis of two entire functions. And from the entire functions, like you, there's no reason to understand why you should put a fraction, but fraction turns out to be there. Yeah. Yes, but that's like in the previous talk, arrows can be in one sense. Yeah, okay, but that's only a coincidence. So it's a phenomenon related to irregularity. Maybe what I can add is that if you want to recover the classical case, in the classical case, you find all exponential factors. Sorry, I'm not used to this remote. You find all exponential factors equal to 0. And actually, in that case, independently of the order of the operator is forced to be 1, and the formal power series actually converges. Okay, so it's really something linked to the irregularity. And okay, so now I want to talk about shifts. So how can I encode in a shift theoretical way this kind of phenomenon? Look again at the Stokes picture. He drew it in a kind of log polar plot because the dotted line is the reference, the 0 in the log polar plot. But I draw it back again here in Cartesian coordinates. It's the same picture as before, but before looking at this picture, maybe I explain. So now I switch a bit. I want to go in the shift setting, but I prefer to do it in the real setting because it's already perfectly reasonable to do it there. Think, if you wish, as Stokes, that now my M is a circle of radius capital C, centered at the origin, so a small circular neighborhood of infinity. Anyway, you take any real analytic manifold, you take an open subset and a function which is continuous and subanalytic on this open subset. To this, I can associate a very simple shift, which I denote by an exponential, because it will really be the exponential. That's a shift on m times a copy of the real line, and I will always denote by t the coordinate on this additional copy. So this is what? This is the shift, which is the constant, the constant shift on the epigraph of phi, actually minus, but doesn't matter, which is a locally closed subanalytic subset in this product. And by this notation, I mean that you continue the shift defined a priori on that set by 0 to the full ambient space. So Deligne was dealing with local systems. Now we are going to deal with what can be called Stokes local system in quotes, because there are several possible different definitions, but I use this definition. I consider shifts which are shifts on the product, which are locally isomorphic to a direct sum of exponentials, so not locally constant, but locally isomorphic to a direct sum of exponentials, not on m times r, sorry, this is a mistake, but locally on m. So they're locally on vertical bands. And I claim that such a shift is precisely encoded by Stokes matrices. Why? Because if you look at the example of Stokes, which was dealing with Airy, then think that you cover the line here by finitely many or whatever, by an open cover. Then on the overlap, if so on each open subset, you can fix an isomorphism from your shift to the normal form, this sum. And then if you want to reconstruct, you need to say how to glue on the cover. And to glue on the cover means that you need to be able to describe the endomorphisms. In the case of Airy, there are only 2 exponentials. So endomorphisms of this kind of shifts. And I claim that since we are dealing with shifts, in this case on a closed subset, if there is a non-trivial morphism from one to the other, necessarily the functions must be related in this form. So if you see according to whether one graph is on top of the other, or maybe if they are not comparable, the matrices are always triangular, remembering this order relation. Okay, so that's a good way of encoding Stokes phenomena in a shift theoretical terms. And fortunately, Tamarkin already did the work for us, because he introduced something that Kashivara and I called enhanced shifts. with a construction that I now quickly recall. So I'm going to consider objects in the derived category, because anyway, there will be derived functors appearing. Again, on the product, m times r. What you need to do in order to make it a tensor category is to change, I mean, it is, but if you want to convenient tensor category for our problem, the only thing you need to do is to change the tensor product by replacing it with an additive convolution, which of course appeared in Javier talk the other day. So the definition is that you have two shifts on m times r, you pull them back on a common ambient space, and then you push forward by the addition. So addition only in the additional variable, note that x is not touched by this operation. And technically speaking, it's the extraordinary push forward. Okay, so you can define a category of so-called enhanced shifts by decreting what? Sorry, let me first point out also this fact. Concerning to this additive convolution, it is clear that for the convolution, the unit is the delta function. So if you take the shift which is concentrated on t equals 0, constant on the base m, then that's a unit. It's also easy to check that fortunately exponentials behave as you expect. So the product gives the sum of the exponents. And in particular, if you take both exponents being 0, you see that e to the 0, which is c t greater or equal than 0, is an idempotent. Okay, so it gives tensoring by this, I mean, convoluting with this gives a projector. And I define the category of enhanced shifts to be only those objects which are stable by this projection. That's not an additional datum, it's only a requirement, because I want that the isomorphism is induced by the natural morphism at the level of exponentials, which is given by inclusion. Okay, so it is an S category because it is naturally embedded into enhanced, I mean, usual shifts are embedded into enhanced one. You simply pull back your shift, which is only on the variable, only on M, you pull it back. And then, as I was mentioning before, concerning the regular case, you want those to be regular in some sense, so you only put the exponential with 0 exponent. That's very natural. And since it is an idempotent, of course, they belong to the category. And they are also endowed with the full set of operations, which will be important for us. Besides this convolution, what you do is you use the usual shift theoretical operations, keeping the additional variable fixed. Okay, then notation back in the complex setting. If you take a meromorphic function, then you can consider the corresponding meromorphic connection whose nabla is d plus df. That's in general irregular. And however, you need a caveat, means be careful in Latin. And you need to be careful because if f minus g is bounded, actually, so if actually it is holomorphic, then in the D-module sense or in the meromorphic connection sense, the two gadgets are isomorphic, but the things that I just defined are not. So it's good, but not completely good. We need to do something else. So this is an explanation of the first adjective that appeared in red, enhanced, and the second was subanalytic. So once again, fortunately, already somebody did the work, Kashivara and Shapira introduced in 2001 this notion of subanalytic shifts. Let me play again this trick of the color code. In the first two lines, if you forget the red, you will just see the definition of a sheaf. A sheaf is just a pre-sheaf on open subset satisfying some sheaf conditions on covers. And now put the red. If you take a full subcategory where you consider only open subsets which are relatively compact and subanalytic, and then if you look only at finite covers, you get another category of sheaves which are called the subanalytic sheaves by Kashivara and Shapira. Again, of course, being a sheaf in the classical sense is more restrictive than being a sheaf in the subanalytic sense. So there is a fully faithful embedding from usual shifts into subanalytic ones. And actually, since subanalytic subsets form a basis of the topology, you can also sheafify. It turns out that this alpha is left adjoint to the embedding, but it's just a sheafification. Yeah. I just wanted to go faster. As you're saying, you can, it's just a particular case of a graph-analytic topology that you can attach to a real analytic manifold. So maybe since you asked, I don't know if anybody knows what subanalytic means. That's something used by Hironaka in his, it's a very nice category, not of open, but in general, a subanalytic subset is something, for example, if you take the image by a proper analytic morphism, the image is subanalytic, and then it is stable by many things like complement, locally finite union, and so on and so forth. Okay. Very important example considered by Kashivara and Shapira is the example of tempered distribution. You take the usual Schwarz distributions on M, and on an open subset, you consider only those that are extendable to the full space. So being in the image means that you can extend it. And if you think a bit, it means that you put some kind of tempered growth condition on the boundary of U. So this is clearly a pre-sheaf in the sense of whatever, even for usual sheaves, but it turns out to be a sheaf in the subanalytic sense, while if you consider it as a sheaf in the usual sense, you lose all growth conditions, and so it's not at all interesting. It's interesting only in this subanalytic world. For example, if you consider the more elementary irregular the module that you can think of, e to the 1 over x in one variable, then we would like to try to compute solutions, so kernel of the corresponding operator x squared dx plus 1 acting on this sheaf. And it turns out that there is a classical component, cx smaller than or equal to 0. Sorry, maybe somebody asked the question, I forgot, I go back. Oh, no, it's here. Yeah, I started to talk about operations, but I didn't finish. So there are the usual operations on the left-hand side, and there are some operation natural on the right-hand side, especially if you think about the graph-analytic topology, pull back and push forward are obvious, also the on. But in general, the embedding does not commute with everything. And so Kashivara and Shapira decided to put a code on those that do not commute. For example, the colimit for usual sheaves is not the same as the colimit for subanalytic, and they put quotes. The inner OM is not the same. They put an I in front because there is something lurking here. Actually, the theory was done in the setting of what they call ind sheaves, so ind objects, and the notations are taken from there. And actually, also the proper direct image that I used already to define the convolution does not commute. Okay, so this quoted limit is the limit in the sense of subanalytic sheaves. And actually, if you want to do this exercise, it's not overly difficult because the solutions are just the function e to the 1 over x. You ask yourself, when is it tempered on an open subset? And the answer is if and only if the origin does not belong to the closure of the intersection of the open with the positive half-line. Okay, so again, looks very nice because you keep track in some sense of the irregularity. You see that, for example, you can prove that when you compute sections on the interval 0, 1, you get 0 here, but not on the left. So you see where the things grow and where they decrease exponentially. But unfortunately, it's again not enough because you see that if instead of 1 over x, I consider 2 over x, the corresponding colimits are cofinal and they give the same answer. So I cannot distinguish between these which at the level of connection are different. Again, not enough. Also, another problem, if you think of irregularity at infinity, like in the Airy case, so e to the x, and you do the same computation, well, since there is this relatively compact assumption here, you can check that in this case, the quoted colimit coincides with the usual one, and so you don't see any information on the growth at plus infinity. So what Kashivara and I needed to do was to merge the two things with one small additional ingredient, which is what we call border spaces. Border spaces are simply a pair of an open subanalytic subset in a real analytic manifold. You need to give a suitable notion of morphism. A morphism between border spaces is just a morphism on the open components with a couple of conditions. First of all, the closure of the graph in the product M Čech times N Čech should be subanalytic, and moreover, the projection from this closure to the first component should be proper. So if you want to think a bit, since it's very fast, just to give a couple of hints. You can think of this as kind of a partial compactification, and you can think of this morphism in algebraic geometry. What's an isomorphism? An isomorphism is kind of birational morphism. You only have an isomorphism at the level of the open components. So a basic example is that if you actually usual spaces are bordered if you don't put any border. So M is just MM. And if you don't put any border, it's not wasted. If you put a border which is empty. Okay, so there are natural morphisms from M to M infinity and from M infinity to M Čech. The first induced by the identity and the second by the embedding. Be careful that thanks to this condition, you cannot do really anything. There are some prescriptions. So you cannot reverse the identity. I mean, you can, of course, reverse the identity at the level of open subset, but not at the level of border spaces. Okay, so now we can consider a kind of variation on the previous slide. Now, if you don't look at the red, I copied the definition of subanalytic sheaf. Now I want to define what's subanalytic on a border space. You simply need to ask the relatively compact and subanalytic condition in the ambient space, in the compactification. And the rest is all the same. So this is better suited because, for example, if you go back to e to the x with the irregular singularity at infinity, now you do detect something happening up at plus infinity. Okay? This colimit is no longer trivial. Okay, so sorry if I didn't ask if there were questions, but I already had some questions. Anyway, I need to go forward and let me merge the two things. So what it means to be enhanced and subanalytic at the same time, it means simply that you do the two operations in combination. So first of all, you consider subanalytic sheaves which are defined not on M, but on M times R. Moreover, you possibly complete M, I mean, possibly put a border on M, but for sure you put a border on infinity. And then you ask that it is stable by the projector. The operations are there. And now I need another notation. I define an exponential with a double vertical line to be the colimit when you do without the vertical line would be just the epigraph of minus phi. So t plus phi greater or equal than 0. And now this graph, I push it higher and higher by translating with a constant. And why do I do that? I do that because I want to solve my first caveat. If I do that now, it is true that for exponents with bounded difference, the corresponding objects are isomorphic, which is good. And also, I solved the second caveat, because now e to the 1 over x is no longer isomorphic to e to the 2 over x, already because we introduced this additional parameter t. So the two systems are no longer confined. And again, there is a natural embedding. The only difference is that I prefer to take the tensor with this new upgraded exponential. Was it too fast? Pi was the projection to the base, but you're right that it's far away. I used it for the embedding, but you're perfectly justified not to remember. I went fast because I don't know how to calibrate time with the slides. So other questions? Once again, maybe quick recall before going to the statement. There is a notion of enhanced sheaves due to the marking, which consists in adding one variable so that you can keep track in some sense of the Stokes phenomena. And the idea is that to a function, you associate an exponential, which is the epigraph. Then there is a second idea, which is the idea of subanalytic sheaves when you can keep track shift theoretically of growth conditions, something that you cannot do with the usual transcendental topology. And then there is a merge of these two things, where the exponentials that you can define seems really to be well suited because they satisfy everything that we need, both for the Stokes phenomena and for things that happen for usual exponentials in the sense of the meromorphic connections. Okay, so now let me go back to this was all in the real setting, dimension 1 mostly, but let me go back to the setting that we need. X is again a complex manifold of arbitrary dimension. If you don't look at the red, you can define, if you wish, holomorphic functions as being the Dolbeault complex with coefficients in whatever you want, but let us say distributions. So a priori, you get an object in the derived category. You still have an action of holomorphic derivatives because here you put d bar, so they commute, it's still a d module. Now, if you put the red piece, you define, by definition, tempered holomorphic functions are the same thing, but the Dolbeault complex is with coefficient in the new gadget that I just discussed. Turns out that this is no longer in general concentrated in degree 0, but who cares? It's an object perfectly well defined of the derived category. Now, usual solutions are morphisms with values in O. Of course, tempered solution will be solutions with value in O10. If now you want to enhance, so this is the subanalytic picture, the enhanced picture, I need to add one variable, but now I am in a complex setting, so I add a complex projective line with a fine coordinate whose real part is my t that Tamarkin added. And I consider the embedding of x times r infinity. R infinity, maybe I didn't read it aloud, it was written in a previous slide, is the border space R considered as an open subset in the real projective line. So I have this one with x times r infinity naturally embeds in the sense of border spaces into x times p. So how can I enhance this tempered guy? What I do is I consider tempered solution of e to the tau. Tau is, so it's something that has irregularity at infinity. And of course, it only concerns the p variable, not the x variable. So if I do, I put in in blue things which are important, but less important than what's in black. So essentially what I do is I consider solution of e to the tau. And then in order to fit into my framework, what do I need to do? First, I pull it back to my R infinity instead of the complex projective line by the extraordinary pullback. And then I project it into the enhanced category. And the two here, I will give, it's technical, but I say a comment in a few minutes. Okay, so this new guy is an object in the derived category of enhanced subanalytic T-modules. And of course, I can consider the corresponding solutions, which amount to compute the solutions with values in this new gadget. But let me rewrite it explicitly. The fundamental thing is that instead of solving M, we are going to solve e to the tau times M. And if you remember the exponential functions in the sense of sheaves, it was the epigraph. The epigraph was something living in t times x, so the t plus phi greater or equal than 0 will correspond precisely to the fact that we put explicitly e to the tau there. For example, if M is e to the f, then this exterior product is e to the tau plus f, whose real part is written here. Okay, so now proposition. If you start from something which is in fact regular, then you don't mess up with what was previously there. The usual holomorphic solution coincide with the tempered one, coincide with this new gadget. And if instead you consider something which is possibly irregular, the most easy example, so the usual e to the f, then you find precisely this one. So once again, let me repeat that by definition, this one corresponds to taking the real part of tau plus f of x smaller than 0. And tau plus f of x is precisely the exponent that you find when you do this operation. Okay? So this is the complex setting. And now I can state the theorem, which is this one. On the row which is below, I just copied the result by Kashivara. I didn't stress in the second slide that, in fact, Kashivara in 84 was able to reconstruct. So not only he can go from holonomic to perverse, but also from perverse back to holonomic. This is the statement in the derived setting, but that's precisely his statement. And then there are the natural embeddings, and a row on top is what we did. So now we have all the gadgets to compute the correct solutions. What we prove is that we have a fully faithful embedding here, but we are also able to reconstruct in a way very similar to what Kashivara did in 84, meaning that natural here means that you can embed holomorphic D-module into things which are not even coherent a priori. But if you start from something which is holonomic, then its solutions recover your D-module, okay? So that's not at all an idea of the proof, but very roughly speaking, what you need to do, already in 84, Kashivara did a kind of devisage to reduce to a normal form already considered by Deligne. Now we need to do a more complicated devisage to reduce to a normal form, which is due to a very deep result by Mochizuki and Kedlaya, which was proved in dimension 2 by Sabah and conjecture in general, which is the higher dimensional analog of Hukuara-Levelt and Turittin. So leaning on this fact, very roughly speaking, since we have all the functoriality, actually you reduce to the previous proposition where this can be checked by hand. Okay, I'm really exaggerating a bit. So let me conclude by giving some more recent contributions. This is a paper which was sitting on the archive since 2013 and then was published after a delay of 3 years in a journal. So in, so I'm going to comment on that. So as I put it there, so if you think on the regular case, which is more familiar, what I wrote here is not at all satisfactory because I would send regular holonomic modules into arbitrary sheaves of C-vector spaces. And that's what I do here. So first of all, instead of considering C constructibility, you can consider something weaker, which is R constructibility. A sheaf is C constructible if it is locally constant along the strata of a complex stratification. You can instead consider a subanalytic stratification in the real set. So this is big, but it's bigger than that one, but it's already smaller than what we had before. So what we can do up here already in the original paper, we defined what it means to be R constructible. Again, still not completely satisfying. Second part, Kashivara, in the regular case, I said was considering here perverse sheaves, which are the T-structure analog of modules here. And you can ask what about T-structures up there. So in the R constructible case, in a second paper, which I wanted to mention here, we did that. So we gave a notion of generalized perversity in this setting, but again, it is too big. The problem is that if you look at T plus real part of F, there is a kind of interplay between real and complex, which we were not able to resolve completely in purely topological terms. So this is still open, but Mochizuki, sitting there, was able to prove something that he called a curve test to describe precisely the essential image. So in dimension 1, people knew everything since the 90s because I have not yet mentioned, but Deligne and then Malgrange gave a complete description of what happens also in the regular case in dimension 1. So leaning on the fact that you can know whatever you want in dimension 1, the result of Mochizuki goes in this direction because he asked himself, if I have something which is enhanced subanalytic, is it in the image or not? I cut it with a line, so with a curve, which is something in dimension 1. There I know precisely if the answer is yes or no. If it is yes for all curves, then it is yes. Of course, it is not completely satisfactory in the sense that, again, we do not have a complete topological description of the image. And finally, always in terms of the description, there is a reinterpretation by Kuwagaki, which might be interesting. So Tamarkin, he was interested, to my knowledge, not in the Stokes phenomena, but in symplectic topology. And the symplectic topology is linked to Kashivara-Shapira microlocal shift theory. And anyway, in symplectic topology, people is used with the Novikov ring, and the idea of Kuwagaki is to reinterpret our construction, not reproof, but reinterpret our construction, instead of adding an additional variable and considering subanalytic sheaves in hiding everything in the coefficients. So instead of taking complex coefficients, it takes a variation of the Novikov ring and is able to give an alternative description of the target. And finally, what's also interesting, there is a notion of Fourier Laplace transform at the level of the modules, which in the case of the Weil algebra is very simple. There is also, since long time ago, a notion of Fourier transform for sheaves due to Sato, but that was in the homogeneous case. Tamarkin had to consider an enhancement of Sato Fourier transform, and what Kashiwara-Shapira proved was that if you consider on one side the Weil Fourier Laplace transform and on the other side the enhanced Sato transform, they correspond completely. So you can do this before passing on the other side of the bridge or whatever. So this was the source of a series of papers on using this topological approach to do computations. Okay, I'll stop here.
Your comments?
Back one.
Yeah, that one. So for the irregular case, we have this reconstructing functor, right? Go back from regular holonomic module to from the rubble shifts to the regular holonomic module. That's
Yes.
the reconstruction from functor, right? So, but for this irregular case, we don't just have the inclusion. So is it possible?
No, you see, on top I put natural. So if
yeah,
you
yeah.
start from something which is holonomic, you find the same. It's a reconstruction functor.
Oh, that's already reconstructed. So for any
So
you have the sub, you can get a D module. Yeah?
from any enhanced, you get a D module without any property at all, but of course you have a structure D hat. But if you start from something which is holonomic, you don't do anything if you follow the two arrows. Okay, taking solution and then taking the reconstruction functor, as the name would suggest, it's a reconstruction. So you start from M and you fall in M.
Any other question? Okay, let's thank speaker again.